Welcome to the IMechE design presentation, where we'll be discussing the main components of the design of our repeatable vehicle. First slide, please. The drive system is run by a geared 12 voltage motor that has a rotational velocity of 3 revs per minute, powered by 6 AA batteries. Moreover, torque is transmitted using a belt drive, as shown in diagram 2. We chose to use a belt drive system rather than using a gear drive system, as finding the gears to our desired specification was difficult, and 3D printing them would have sacrificed accuracy. In addition, a belt drive is more cost efficient without compromising torque transfer efficiency. Next slide, please. Diagram 4 demonstrates the drive system assembly. Compound gears were used in order to achieve the desired gear ratio of 1:16, where there is a step down by a factor of half from the motor gear to the stopper gear, which is necessary for measuring the distance. That will be discussed later. Then there is a step up by a factor of 4 until the last 2 gears, where there is a step up by a factor of 2. This gear setup and ratio allows the vehicle to complete the entire maneuver in approximately 40 seconds. Next slide, please.
So in our power circuit consists of 3 switches: the SPST switch, which turns on the vehicle; the SPDT switch, which switches off the vehicle when it returns to its initial position; and the reversing mechanism is achieved through the DPDT switch, also known as the double pole double throw switch, and its purpose is to reverse the direction of circuits at the motor. And on the left diagram, we can see 3 stages of our circuits, and the wires that are in gray denotes the wires that are deactivated. And we can see how the activation of the DPDT switch actually deactivates certain parts of the circuit so that the direction of current through the motor is reversed. And on the right diagram, we can see a real setup of our circuit in relation to the schematic of the circuit.
So now it's the distance measurement principle. The basic principle of distance measuring is displayed at the right. So in short, we have like a stopper wheel or the big wheel that won't rotate a full revolution on the way to the wall. Therefore, on the journey backward, this stopper wheel will be caught by the stopper to stop the wheel from rotating any further. Therefore, cut off the movement of the vehicle. Besides, we have installed the SPDT switch to shut the vehicle down when the stopper is caught. We have calculated that if the wheel has a radius of 4 centimeters, the gearing ratio must be 1:32 to cover the 4-meter one-way journey to the wall. In reality, given the constraints of the tool available to us, it is not practical to manufacture 2 wheels with such high gearing ratios. Therefore, we decided to use the compound gear or pulley system to achieve it. I mean, dividing 1:32 to 1 times 4 times 4 times 2. The hollow gear will be the stopper gear in this case. Next page, please. Here is how it looks when the whole system is installed inside the chassis.
Straight line motion. To travel in a straight line, the center of mass of the vehicle needs to be aligned with the center of mass of the chassis. To further stabilize the vehicle, we will fix the wheels to the road using superglue on both sides of the wheel. Next slide, please. The rods connecting the wheels are made from aluminium, which is light and strong, with a tensile strength of 90 megapascal. It can support the wheels and not bend during multiple runs. The chassis is made from pine wood, with a bending strength of 60 megapascal. During the impact, the maximum deformation of the spring is 3.4 millimeter. The length of the switch is 5 millimeter, so the chassis will not touch the wall. In the figure on the left, you can see the stress simulation of the spring, with a spring rate of 1700 Newton per meter. The colored region shows the maximum stress applied to the spring when the spring collides with the wall. Thank you.